In this video, we'll continue our discussion of sampling distributions, moving outside of the mean discussion and moving into other population parameters that we can make sampling distributions for, such as the population proportion. We'll also talk a little bit about some different sampling designs we can do very quickly as we continue this review. So similar to the population proportion, similar to the population mean is the population proportion. And actually this section of the slides and hopefully this video is going to be much quicker than the last video because the proportion is actually very similar to the mean. We get a sample, we can't estimate the population directly. We calculate the proportion from the sample data, and then we use that estimated proportion. And again, I like p hat as opposed to p bar, but we'll stay with the textbook notation through the notes anyway. We use the estimated value from the sample to guess at the population value from the population. So sampling distributions, and again, hopefully this is a good first introduction to this concept, that sampling distributions can be constructed for any population parameter. So in this particular case, we can have a sampling distribution for the estimate of the population parameter p for the proportion. Now the sampling distributions do change for different sample sizes, so as my sample size changes, then I'm going to get a slightly different sampling distribution. We saw that previously. It's nothing crazy. All that changes is that the standard deviation goes down. That standard error that we talked about goes down as your sample size increases. That's the change when I say these sampling distributions change based on the sample size. All I'm saying is that as we have higher and higher samples, our estimates get more and more precise. That's it. Similar to the mean, the expected value or the average, if I did a whole bunch of different samples and found their estimated proportions, is the actual population proportion. Now this one's a little different, the standard deviation of the population proportion. So we have p times 1 minus p over n, that's the infinite population value. For the finite population, we still have that same finite population correction factor that's multiplied into here. Again, typically people are going to use the infinite population one unless they have a good reason to include the finite population correction factor. I should note here, though, that it's never a bad thing to include the finite population correction factor. Like, if you know capital N, this will not hurt your analysis. So I say typically we do this one. We do it because it's easier, not necessarily because it's statistically better. This will never hurt. And as capital N goes to infinity, these two things go to each other. So there's never anything wrong with including this when you quote unquote shouldn't or didn't need to. It's just that you did a little bit of extra work. That's the only bad thing that would happen. So if in doubt, you can definitely drop this in and keep it in. And in fact, there's a whole sub-branch of statistics that talks about doing this and talks about some modifications to traditional statistics, which often tend to assume infinite populations. And how can we add these concepts like the finite population correction factor into those? Now the big difference between the proportion and the mean is the standard deviation calculation. So this standard error, the standard deviation of the sampling distribution of proportions. Again, that's a very long thing to say, so I'll just say standard error, but the standard error for the proportion, not the standard error for the mean. The standard error for the proportion is different than the standard error for the mean, so that's the big difference. The second big difference is this idea of the distribution. So we need the sample size to be large enough to satisfy these two conditions, and that is that the sample size times p is bigger than 5, and the sample size times 1 minus p. Sometimes you'll hear me call 1 minus pq. It's the probability of not getting the expected outcome, q. It's just quicker to write than 1 minus p. But np needs to be greater than or equal to 5, and nq, or n times 1 minus p, needs to be greater than or equal to 5. That is honestly just to, when we draw the picture, give us some room in the tails, the upper and the lower tail. to make sure that we have enough space for these things to be um, accurately seen. So when this happens, then we can absolutely use the normal approximation in the same way that we always do. And when it doesn't, we want to be a little bit more hesitant about that. Note that the way that this would not happen is if n is very small, so we don't have a very large sample size. Again, above 30, that tends to be pretty good, or above 50. Or if p, or 1 minus p, is particularly small. So 1 minus p is small when p is large. So if p is very, very close to 0 or very, very close to 1, then this is not going to, then we're going to need a very large sample size for this to work. When p is in the middle, we don't need a particularly large sample size. So let's look at 0.5. How big of a sample size do we need if p is 0.5? Well, 10 times 0.5 is greater than or equal to 5, and 10 times 1 minus 0.5, 1 minus 0.5 is just 0.5, so 10 times 0.5 again is greater than or equal to 5. So if p is right in the middle, we only need a sample size of 10 to satisfy this condition. If p is near the edges, we may need a much, much larger sample size to satisfy that. So in this case, we've got 72% of the prospective students. What's the probability that a simple random sample will be within 5% of the actual proportion? So 0.05 of the actual proportion, or 5%. Well, in this particular case, we've got a sample size of 30, p equals 0.72, so we just plug in this information. First, we're going to check and make sure that these values are greater than 5 so that we can continue with our normal estimate. After this, if we can continue with our normal estimate, we can go to the z-score to calculate those percentages again. So we've got our standard error of the proportion is 0.082, and then we take that standard error and use that as the standard deviation for the proportion. So we've got the observed mean proportion minus the population mean proportion divided by the standard error of proportion. And again, when do we do standard error of proportion versus individual proportion? We do standard error proportion when we're looking at sample proportions. I took a sample of size 30 and found the proportion. As opposed to, we'd use the individual standard deviation of the proportion when I am doing individual values. So that's what's changing what our denominator is do I use the standard error? I would do that if I'm looking at a sample proportion. Or do I use the standard deviation? I do that when I'm looking at individual values. We're going to do the exact same thing as we did before. We find the upper value, 0.72, and again, that's the area all on the left side here, but we need to make a cut and then cancel out the area that's too far to the left because we just want to go down by 0.5 down. So we can do this in a table or in R or in Excel. Find that value. We're going to do the same thing. The lower value of the interval we're interested in, 0.67 minus 0.72 over the standard error of the proportion gives us negative 0.6. And then we find that on the table or in R or in Excel, the area of 0.2709, and then we subtract the 2 to get the area in the middle. So what does this mean? This is the probability is about 46%. That would be within 5% of the actual population proportion of individuals that want on-campus housing. And again, I know I'm going through this pretty fast. This is supposed to be a review. If you have any questions, please feel free to reach out. Big takeaways for this class. What is a sampling distribution? How does it relate to the original distribution of the data? And the idea that we can do sampling distributions of a bunch of different parameters. All right, so we're going to close out this section on sampling by talking about actual sampling methods. Everything we've talked about right now has been the simple random sample where we just randomly pick people from the population, but there's a bunch of other sampling methods. Now this is going to be extraordinarily quick, and there are whole classes that I have taught and that you can take that are devoted purely to sampling. Each of these sampling methods does something slightly different than one another. We'll talk about them, but each of them offers a little bit more efficiency in its own little world. So specifically these top three, I should say. So when we are talking about using some of these, that's the purpose of them, is that we can use the same number of data points, but if we collect them slightly differently or using a little bit of a more clever collection technique, we actually get a more precise estimate. In some cases, we get much more precise estimates or much, much better guesses just by being a little bit more intentional about who we collect data from. So again, we're not going to go into the weeds on this, but we will quickly walk through these. So stratified random sampling, we first divide the population into strata. So we split it out based on whatever characteristic you want. One good university one is like freshmen, sophomores, juniors, and seniors. And so when we do this, what we're looking for is that within each of the groups, the group themselves, like the freshmen, all of the freshmen are pretty similar. All of the sophomores are pretty similar. So that's what we mean by the homogeneous group. When we split it based on the strata, we want everybody in the strata to be as similar as possible. And when that happens, that's when we're going to see the benefits of a stratified random sampling technique. So if we have good strata, then this is going to give us a lot of advantage. So yeah, we can see we've got a lot more precision than the simple random sampling. What this turns into is either a more precise estimate with the same sample size, or we can use a smaller sample size to get the same level of precision, whichever is more advantageous in the particular situation. So yeah, whatever you can split based on whatever variable you're interested in, but what you're looking for is to split on a variable where each of the groups are really similar on the outcome you're interested in within those groups. So that's the goal of stratified. Cluster is kind of the opposite. We're still going to split, excuse me, we're still going to split on some level of groups. But in this case, what we want is that for everybody in the group to be as different as possible. So cluster sampling, I like to think of as everybody in their cluster is like their own little world with all of the diversity as possible. And then the differences between the clusters, we want to be as little as possible. So a small scale version of the population, everybody within their own world. We want as much variability within the cluster as possible. But we want very, very little variability between the clusters. That's the goal of cluster sampling. So oftentimes these are used in geographical situations, geographical clusters. And so when that makes sense, it actually can save you a whole lot of time and money. Another one to kind of think about is like a classroom. So instead of randomly sampling 900 students on campus where I have to go hunt them all down in each of their different classes, it may be much, much more efficient for me to walk into one classroom, hand out a survey and collect some data, and then walk into a second classroom and hand out a survey. I go to two places. Depending on the size of the class, I could easily get 60 respondents. And I only went to two places, as opposed to if I go each place for a single student, I would have to go to 60 different locations for 60 different students if I were doing it with random sampling. So cluster sampling is primarily about the convenience of the sampling. And again, if we have a lot of homogeneity within the sample itself, a lot of variability within the sample itself, and then not too much different between the clusters, we get some good results. Generally requires a larger total sample size. It depends on, it really depends on how your population is distributed and where that variability comes from. Systematic sampling. This one's kind of interesting and is used surprisingly often. So I call it the nth sampling, nth sampling, because you take every 20th person or every 30th person or whatever from a list, and that's what systematic sampling is you take a certain amount of people from a particular list. Interestingly, this actually aligns directly with the cluster sampling in terms of its estimates. So in this case, every 100th listing in a phone book would be how we could do systematic sampling. And it does tend to be a little bit easier than using a simple random sample where I have to, the numbers aren't necessarily equally spaced. Actually, so let's pause here. So these are three of the methods that are probably the most common methods that would be considered good practice for sampling. It is important to say, so please take a moment, stop texting on your phone or whatever else you're doing, if you're doing that, while listening and hear this. For these different sampling techniques, you have to use different equations for even basic statistics. This is expanded upon in depth if you ever take a class on this. We will talk through those. We'll talk about how they're derived, etc. But please don't implement something like a cluster sampling or a stratified sampling thinking, oh my goodness, Dr. Florence said, well, if I do this, I'm going to be way more precise. It doesn't work like that. You have to use a different formulation of even basic statistics like calculating a mean or a variance or a standard deviation. You can't just add up the data and divide by the number of numbers you have anymore. So that's another cost of these sampling methods, is that the analytical statistics actually become slightly more complicated. And as you get more and more complicated sampling techniques, calculations of even basic statistics become more and more and more complicated. Until at some point they become just very almost painful to do, and can really only be done by experts. And even then, I have gone and looked at some surveys that have used extraordinarily complex sampling techniques, and I could probably put something together that might be a good mean. I mean, mean is just the most basic statistic I can think of. I could try to calculate a mean. I might still be wrong. I wouldn't trust that on some of these more complex designs without speaking to the person who put the design together. And it just comes from the fact that when we make these calculations, we have to account for the different kind of sampling designs. So do be aware of that these sampling designs are really cool. They are very helpful. They do require a slightly different calculation of some basic statistics. And with the three sampling designs we've talked about, it's not too bad. In fact, depending on a software, you might even be able to have software that does it for you. As you get more and more fancy, though, it becomes more and more difficult. Convenient sample. This is probably the most common sample ever to be used. And this example is probably the most common example. I used to joke with some of my friends that 70% of applied research is just done on student volunteers, specifically if you see of undergraduates. So if you ever read a study and see it was conducted with undergraduates and wasn't about undergraduate education or something that is specifically related to undergraduate students, this is probably what happened. You had a professor who was looking for a study and needed people to answer their survey and got some students to do it. Convenient sample literally is just you pick people who are really convenient to use, such as a class, or maybe you go to a friend's class. This can be professors or students. Hey, I've got a friend in this business, so I'm going to go talk to them. The problem with this is that it's really difficult to determine how representative of a more general population the group is that you got. So if I go and just find a random store that a buddy owns and say, hey, can I take a sample of your people? And I'm trying to imply that, or infer that any values calculated with this sample applies to everybody in the world, it's really tough to make that connection, and it's really tough to make that claim. The term for this is generalizability. How much do your results connect with everybody else? And the generalizability of studies that use convenience samples is always questionable. Can you discuss that? Can we potentially use that? Absolutely. People do it all the time. But it's certainly much more questionable than something that used a randomized style. Judgment sampling is something where we intentionally make a call about including particular individuals. Now, this sounds kind of like convenience sampling, and actually, and am sorry to say this, but sometimes researchers do a convenience sample and try to convince everybody it was actually a judgment sample. So I have my best friend's business, and I'm gonna go do a sample out there. But there's a really good reason that I did that. In my professional opinion, that was the best store to use. When in actuality, it was just one that a friend had, and it was really easy to do. Um, Judgment sampling in its purest form is much more specific than this. I'm looking at the entire population, and I pick the best participants, or the in some way. Maybe it's the worst participants, but I pick the most desirable participants for my study using this judgment sample. And maybe what's most desirable is to have individuals across a wide range of different characteristics. Or maybe it's to have individuals who all have the same characteristic in common, or are all in this particular characteristic range. So however you break it down, you have an individual who is extremely knowledgeable on the subject to make picks about the people who are going to be pulled into the sample. I really don't like this example. I guess it's okay, because I wouldn't say that a reporter is the person most knowledgeable on the subject of the Senate, right? But maybe we had a unbiased political science expert. That person might be a good person to pick 3 or 4 senators to pick out the Senate. So that would be a good example of what we're talking about. They say it's relatively easy. It depends. It can be really hard to find knowledgeable people. And this disadvantage is also the advantage to me. And it's appropriate to be listed in the disadvantages here. But the quality of the sample can be much better than randomized data sometimes. It can also be much worse. It really, really, really depends. So if I've got a really, really good person doing a judgment sample, my data is going to be way better. I'm going to have way better quality of participants in my study, and I might have a lot better information that I can generalize based on the study. But if the person really has no idea, then often it turns into nothing more than a poorly designed random sample or a convenience sample. And in those cases, in both cases, a well-designed random sample would have been better. So these probability sampling methods are always recommended just because mathematically they're easy. I have to tell you they're recommended because that's what every other stats person would say. But again, in honesty, if I had a really good person for a judgment sample, depending on the study I was doing, it really depends. It really depends. I would not say that's a bad thing because there are certain cases where I would much prefer a judgment sample versus a probability sampling method. I will say, though, that by and large, these probability sampling methods are far more widely accepted because they are far less easy to mess up. If you use a random number generator, you used a random number generator. You can't mess that up. Well, I guess you could, but hopefully you wouldn't mess that up. It's harder to mess up than having a person whose best judgment may not be completely unbiased or something like that. One benefit of using these probability methods is that we're able to evaluate the goodness of the sample. And by goodness of the sample, all we mean here is that standard error. I can't calculate a good, reliable standard error for a judgment sample or a convenience sample. That's the whole problem. But when I use a probability sampling method, I absolutely can calculate that standard error, which tells me what the variability of my estimate is. And this is huge. Again, this connects to the rest of statistics that we'll be talking about in this course. This idea that we have to use good sampling methods, and in this course we'll pretty much stick with simple random samples. Check out a sampling course to talk about these other types of sampling methods and what you can do for that. But that using these types of methods allow me to estimate the error, how wrong my estimate is. Like, that is a really cool idea, the idea that I'm going to gather 20 people. I'm going to make an estimate of the population, and I'm going to have a guess as to how far off that estimate would be. That's a really, really, really useful property because it allows us to give a good self-check and come up with some reasonable ranges for the outcome that we may have, and we're going to talk about that in the next lecture. Again, this is just not possible with a non-probability sampling method. And again, judgment sampling methods can be really good in certain circumstances, but if my goal is to have an estimate of my own error, of the how messed up my own guess might be, judgment sample just can't work for that. I'd need something that uses probability involved with the sampling method and relates that sample in some way back to the population in terms of the probability of individuals being selected. All right, so this is the end of this particular chapter's review. I apologize for the length of this one. We captured a lot, and again, this is several weeks of material that we're slamming into, I guess, an hour with these videos together. But please feel free to reach out if you have any questions at all. Again, for the rest of class, the big thing to take away is we'll probably be using simple random samples and take away this idea of the sampling distribution, because that will come back, and we will use the term standard error often through the rest of this class. In the next video, we'll be covering confidence intervals, which give us those reasonable ranges of values that the parameter might fall in. And again, it uses this idea of standard error and how far off is our guess, potentially, how much error does our guess have. And it uses those in hopefully creative and intelligent ways so that we can make even better guesses and let everybody know who's reading our results know both what our best guess is and how much indecision or how much gray area there is with our best guesses. So that'll be the next video.